This section introduces the core problem: reducing the dimensionality of a high-dimensional dataset, 1000 features, using scikit-learns. We'll explore different projection techniques, Gaussian and sparse, and their effects on data sparsity. It sets the stage for the multiple-choice question that follows. This is like deciding the best way to compress a large image while retaining its essential features. This poses a multiple-choice question about the class in scikit-learns module. Specifically, it asks which statements about using Gaussian and sparse components for dimensionality reduction are accurate. We need to assess the truthfulness of 4 statements based on the characteristics of each projection method. Think of it as a quiz to test your knowledge of different data compression methods. This statement claims that the sparse component of is computationally faster for high-dimensional data. This is because sparse matrices contain many zeros, reducing computations compared to dense, Gaussian matrices which have fewer zeros. Imagine sorting a large pile of papers, one pile mostly empty, sparse, the other pile full, Gaussian. Which pile is quicker to sort? This statement suggests that the sparse projection method inherently creates a dataset with more zeros than the Gaussian method. This aligns with the definition of sparsity. Think about it like using a sieve to filter out some data. Sparse projection acts like a finer sieve. This refers to a random projection technique using a dense Gaussian matrix. In simpler terms, it's a dimensionality reduction method that uses a matrix filled with normally distributed random numbers. These matrices have few or no zero values, hence they are dense. This refers to a random projection technique utilizing a sparse matrix. The matrix mostly contains zeros, a few elements hold non-zero values. This results in reduced computational costs. Think of it as a more efficient way to reduce dimensions by keeping only the most important information and removing redundant data. Hey Vamsi, let's dive into the core of this question. This line introduces the main topic, comparing 2 techniques, Gaussian and sparse, for random projection in dimensionality reduction. We're going to analyze how each approach affects the final data. Think of it like choosing different paths through a maze. Both get you to the destination, but one might be faster or cleaner. This line sets the stage for a multiple-choice quiz. It's asking us to identify which statements accurately describe the properties of Gaussian and sparse random projections using a popular machine learning library, scikit-learn. Each statement will present a comparison of these 2 techniques. This statement is about efficiency. Sparse projections use a matrix with mostly zeros. Imagine a huge spreadsheet, mostly blank. Doing calculations is quicker with fewer numbers. This makes it particularly better for large datasets, lots of features. Think of sparsity as how many zeros you have. The sparse method builds this sparsity into the core algorithm. The resulting data after projection will naturally have a larger number of zeros compared to the denser data from the Gaussian method. This claims both methods give the same accuracy when reconstructing the data after reducing its dimensions. This is generally true. They represent a trade-off. Sparse is faster, but Gaussian may preserve more of the original data's characteristics. Okay, Vamsi, let's break down this question about dimensionality reduction using scikit-learn's _random_projection. We are comparing 2 methods, Gaussian and sparse. The goal is to figure out which statements correctly describe their differences and characteristics. Exciting stuff. We'll examine each statement carefully. The key concepts are dimensionality reduction itself, random projection as a technique, and the specifics of Gaussian versus sparse random projection matrix types. This statement focuses on computational efficiency. Remember, a sparse matrix has many zero entries. For high-dimensional data, lots of features, using a sparse matrix for projection means significantly fewer calculations are needed. This leads to faster processing times. Think about it like this. If you have a giant spreadsheet mostly filled with zeros, you don't need to process every single cell. You can skip the zeros. That is the advantage of sparse matrix representation. Therefore, statement B is generally true. This statement talks about the sparsity of the asterisk result of the projection. Since the sparse method uses a sparse matrix, lots of zeros, to project the data, the resulting projected dataset will naturally have more zeros itself. It'll be sparser. The Gaussian method, on the other hand, uses a dense matrix, fewer zeros, resulting in a denser projected dataset. Hence, statement C is also correct. In conclusion, VOMC, based on our analysis, statements B and C accurately describe the characteristics of sparse and Gaussian components in scikit-learn's _random_projection. Let me know if you have more questions. This problem challenges us to understand how scikit-learn's random projection works with different methods, namely the Gaussian and sparse components, for dimensionality reduction. We'll explore how these methods impact data sparsity and computational efficiency in a high-dimensional dataset, 1,000 features. This is the core question. We need to evaluate 4 statements, A, B, C, D, about the Gaussian and sparse random projection methods in scikit-learn to determine their accuracy. Each statement presents a different claim regarding these methods, focusing on variance preservation, computational efficiency, data sparsity, and reconstruction accuracy. This section would ideally contain a table summarizing the key differences between the Gaussian and sparse random projection methods. It could compare things like computational cost, sparsity of the output matrix, variance preservation, and reconstruction accuracy. We can infer the comparison from the preceding text.